All right, welcome. So today we're going to be looking at something that's similar to what we were doing in the past couple videos, only this time instead of looking at measures of arcs and angles, we're going to be looking at lengths of segments within the circle and without. So we're going to be using our chords and our tangent lines and our secant lines to set up equations to solve for sections of those lines. In the first example we're looking at, we'll notice that we have two chords that intersect inside of the circle. So if the lines intersect within the circle, we will solve for the individual portions by multiplying the sections of each line. So AB times BC should give us the same value as DB times BE in the example in the box. So in our first practice example, it tells us that we are looking for the value of x. We notice we have two chords that intersect, and we know that anytime the chords intersect within the circle, the product of the sections of each chord should be equal. So if we take and multiply 10 times x, that should be the same value as 5 times 12. So now that we have our equation, we solve. 10x is equal to 60, which means x must be equal to 6. Part B, we're going to do the same thing, only our equation is going to be a little bit more complicated. So we have x times x plus 10 is equal to x plus 1 times x plus 8. And so now we just use a little bit of algebra, use our distributive property, to solve the equation. So we notice that there's an x squared on both sides of the equation. So that means we can cancel it out. Simplify here. Which means that x must equal 8. Alright, so in our next example, we're going to use the same rule. The rainbow is going to represent a portion of a circle. We need to solve for the radius of that circle. So this will be much easier to see if we draw the circle as a whole. And what I'm going to do over here is just draw myself a little circle. Circular, there we go. We've got a chord going across here. We know that the rainbow is going to be this top portion up here And then we need a line segment going down. Because of the way we had everything set up on the previous problem, what I'm going to do is make sure that my line crosses all the way through the center of the circle, and they marked this guy as a right angle. Alright, so if we label everything, we've got the 5 miles going across and the 0.7 miles on the inside. Because this is a right angle, we remember that the chord is being bisected. And the pink chord must be the diameter of the circle. So we notice the only thing we don't have filled in is this part right here. So since the chords meet inside of the circle, multiplying the parts of one chord should give me the same thing as multiplying the parts of the other chord. So 0.7 times x equals 2.5 times 2.5, which is the same as 2.5 squared. Alright, so we go back to what we were looking for, and we need to know the radius of the circle. Well, I don't know exactly where the center is, but I do know that if I can get the full diameter, I can use that to find the radius. And also, if I combine the 0.7 and the x, that would give me the full diameter. So diameter is 8.93 plus 0.7. And of course, to get the radius, we will just take our diameter and divide it in half. Therefore, the radius of the circle must be about 4.81 miles. Alright, so our next theorem is going to talk about what happens when you have two lines intersecting outside of the circle. So unlike the chords that intersect on the inside, when the lines meet on the outside of the circle, instead of multiplying the pieces of the line, we're going to multiply the outside section times the total length of each segment. Alright, so let's see what that looks like in an example. So we look at our circle, and we see that the two secant lines intersect at point J. So for the first section, the outside portion is 8, and the total length is x plus 8. The other line from L to J, the external portion is 6. And the external portion is 16. Now that we have our equation, go through and solve. And there we go. For our final theorem, it looks like a different formula, but the pattern that we're following is actually the same. Right? So we notice the only difference here is that one of the segments is entirely out of the circle. Right? So instead of having two secant lines, we have one secant line and one tangent line. So when we're setting this up, we're going to follow the same rule as before. So the external portion is x. Total length is x plus 7. For the tangent line, the external portion is 8. And the entire length of the segment is 8 as well. So all we have to do here is simplify by distributing. So unfortunately, our x squared will not cancel out this time. So we're going to have to solve this like a quadratic, which means we need everything to be on the same side as the x squared. We also know that we need to attempt to factor this by looking at things that would multiply to make negative 64 and add to 7. So the things that will multiply to 64 are as follows: 1 and 64, 2 and 32, 4 and 16, 8 and 8. Making one of them negative and then adding what I get, I need to look at the total. So if I do negative 1 plus 64, that's 63. 1 minus 64 is negative 63. That's not going to work. 2 and 32 have a difference of 30. 4 and 16 have a difference of 12. And then 8 and 8 would give me 0, none of which are 7. So this will not factor, which means I'm going to need to use either the quadratic formula or I'm going to need to solve it on my calculator. So for the sake of time, I'm going to go ahead and just solve it using my graphing calculator. I'm going to put x squared plus 7x minus 64 into y1, put 0 into y2, and then use the intersect function of the calculator found by pressing second and then calc and then intersect to get the total, or to get rather the point where the parabola meets the x-axis. And it tells me that that happens at x equals 5.23. There's also a negative solution, but it wouldn't make sense for RQ to be a negative number, so that's got to be the correct answer. And that's all we have for today. I will see you guys next time.